a window may have popped up. Okay, great. So we're very happy to have our two speakers today. Our first speaker will be Xue-Mei Li from Imperial, and she'll be talking about toward an effective theory for non-Markovian multi-scale stochastic systems. So thanks, I'll hand it off to you.
Thank you, AJ, for the introduction, and thank both of you for David and AJ for the invitation, which I'm very happy to have a chance to speak here. So what I'm going to do is more like an invitation to this new direction rather than trying to give a comprehensive I'm not trying to give a comprehensive talk on this, but I hope I do talk about something to interest you. Now, there are two things I want to smash them together. One is the correlation in noise. So if you take a stochastic process, you're interested to see whether it's correlated between two different times or not. A wet noise are not correlated in time, and the chaos is there. But others could be correlated. If you look at time series data for various things which we need to model, we see autocorrelations. But in E2 calculus at SDE, the whole theory is based on the decorrelation white noise. Now, so one way, experimental way to deal with it is to take out the process everybody knows, understand well. That's the fractional Brownian motion. So, Volterra process as well. Now, if you see wet noise, derivative Wiener process. Wiener process is correlated. The increment are not correlated. That's the derivative part. And if we integrate the Wiener process, the wet noise out, we get a Brownian motion. That's correlated. And same thing if you have this, I don't know whether you see the hand I move. In the integrand, if you have a Fs, this object, the correlated, but it also keeps some of the independent increment property. But a fraction Brownian motion are similar, but it has a nice part. So on the right-hand side, the second term, and this is the integral from 0 to t of Wiener process with a kernel. So it's like the one we talked before. But then the first term is a bit more involved. It takes the whole history from -infinity to 0 of the Wiener process. So that's the one which causing more nasty correlations, or maybe good correlation if we wanted to have a correlation, but it's the one causing more difficulty. And this stage, before I introduce more processes we are correlated, I would like to compare and review E2 Wiener chaos expansion for L2 random variable. So if you take a L2 random variable, which is xt, I fix the t, and that it can be expressed as expectation, and the integral of determines function with respect to the Wiener process, and then iterated the integral. So the terms become progressively more chaotic, constant, Gaussian, and non-Gaussian. So a fraction Brownian motion is still a Gaussian process. The next one, I would like to talk about the self-similarity. Self-similarity is a very good property for an integrator. So it's easy for us to maneuver. Also, it comes very often from a scaling limit in statistical mechanics. This is sort of an interesting process. Fraction Brownian motion is a good one. It's a good prototype process we could work with. And a similar one in the M scales is called Hermite processes. So they share the same property as a fractional Brownian motion, self-similar, stationary increment, and has the covariance of the same structure. So the covariance between two different times, the correlation decays as the order 2h minus 2. So if h is smaller, it decays faster, otherwise it decays a bit slower. If we have a Gaussian stationary sequence with a slowly decaying correlation, so if you have a Gaussian stationary sequence, you take a lot of large numbers, central limit theorem, you get a Gaussian process, you can apply Dansk type invariant principle, get a process out of it, a Brownian motion. If they are correlated too much, what you get is a Hermite process. The first example was given by Rosenblatt. So for m equal to 2, it's called the Rosenblatt process. And there's a whole industry of people working on that. So there's Dobruschen, Major, Takubai, Sugilis, PPRs, Tutor, Embrace, Jema. There's lots of them. I cannot possibly put it there. I'm just saying it's not new for a topic. It's people being working on that. Another family is called moving average. So you take a kernel, you integrate it with its weighted average along the path of a Hermite process, and other funny fraction Brownian motions for each big than one. Now, multi-scale is very much another prevalent phenomenon, because if you have lots of different objects interacting, influence each other in a random way, but they don't move with the same speed. You can think about weather and climate, as in Klaus-Hausmann's program. Weather is moving very fast in a short time, the climate move very slow, but they influence each other. Now, from mathematical point of view, how do we see multi-scale? What we do is we suppose you have a process on a space called P. And this map of P from P to M can think it as a projection or other objects. And suppose your process is invariant for the P. P doesn't change along the solution. Now we could do a perturbation, or called orthogonal perturbation. Then your new perturbed process, if you apply the P to it, it would move very slow, like epsilon small. Now, if you want to see something changes, we have to look at the larger time scale 1 over epsilon. So we're playing 2 time scales. The epsilon is a separation scale. So typical example, which I would take a famous Friendly and Wenzel theory. You take a Hamiltonian function, you look at the Hamiltonian system given by the skew gradient of H, then adding a little bit of perturbation for Brownian motion. Then you look at the energy function, the evolution of the energy along the solution should be Z there. And then if you can take action angle components, you have the theta, the angle. And if you start with the energy level without perturbation, stay there, but with perturbation is move out, but very slowly, but the angle component will be very fast. So you have a slow, fast system. Now, so what I'm going to start with is a set of equations with a slow, fast already separated. You can see the speed difference. X has input from Y with noise psi t. And the Y has some its own time scale. So Y epsilon is YT over epsilon. And YT solved another equation with input from X and another noise 8. So typically we take set 8 being independent. And so that's interacting full feedback, slow, fast system. You could think of multiple, even more scales, but it's not, there's no point to take anything slower than X, because you typically we know which one we're interested in. If I'm interested in X, something moves slower than X, it can be treated as a constant. And so then we pick up the other one, the very fast one, and to see the interaction. Okay, so the aim is at the scale of X, we want to see how it changes when the epsilon go down to 0. For this, the Y would be moving around so fast. It's not possible to track where Y is, and it's not interesting for us to track where it is. What we really want to see is to see through what's the effect Y gives X. And that is let epsilon go to 0, maybe xt epsilon is approximated by another equation, and this equation called the effective motion. So that's what we wanted. If we started a system with Markovan perturbation perturbed a little bit as before, then the slow and the fast would be Markovan. So that's a typical thing which has been done so far. And let me give you another example to interest you. So this famous Naessens-Langevin model. So you take a particle derivatives velocity v, and the v is has a friction and is subject to some random influence with mass epsilon. We're thinking the mass is very small in this case. Then xt converges, then xt converges. I'm not sure where I put xt over epsilon. So xt converges to a Brownian motion. You can see that quite easily because xt is the integral of v. The integral of v from the right-hand side is just epsilon v plus w. So you take epsilon, go to 0, you convert it to Brownian motion. Now, we could turn this into a slow, fast system in the form I gave you. So this one is not in the right form because I divided by epsilon. On the right-hand side, I have 1-1 scaling between time and Brownian motion. So it's not the correct one. So what we can do, we can rescale, reshape the v, and give it a new variable called y. And that y would be given by a diffusion equation, and the x is given by 1 over square epsilon y epsilon t over epsilon. So y is moving very fast, it appears there, there's a bit of scaling. And that's a typical so-called diffusion equation format. So that's another example how we see this process is coming in. Now, what we want is to put the two topics I have been discussing together. So we have a x equation, a y equation, they interact, and the y, actually, sorry, I shouldn't have had the epsilon minus half here because I doubled the 1 over epsilon. I should have yt epsilon, then yt solving this equation. Sorry about that. And so this look a bit complicated. So I'm going to take, for example, both of them could be a fraction Brownian motion, or one of them could be a Wiener process. I take a fraction Brownian motion when the Hirsch parameter h and h prime to be half, and that's a Brownian motion. Now, this is a bit confusing to start with. It's just that we don't know where to start from. And to make life easy, I just take YT to be a stationary process with low mu. It's given. So it doesn't solve equation, it doesn't involve the X. And in this case, we will take a bar F, denote the average of F with respect to mu. So then to solve this problem, we're concerned with two problems. One is dynamical problem. That is when the fast motion is driven by fractional Brownian motion. Right? So the whole theory would depend on a Gaudic theorem of the fast motion. And basically, if it's a Gaudic, it will go everywhere, and time average is space average. Because we're talking about in the time interval, when you need the time for the slow is very fast for y. Y would have been everywhere. You should have seen the average effect. The question is how the average is taking effect. This is naive way. This is some more complicated way. And the question is how it would be doing. And then, of course, how does the Y process, if it's sort of stationary, even for the stationary, you're talking about what's the autocorrelation between Y. Okay? If Y solving an equation like the Einstein-Uhlenbeck process, everything converges to each other very quickly, any solutions, do you say, does the autocorrelation disappear? In fact, it doesn't. So that's one of the problems. The other one is non-stationary problem. That's even more interesting. And how, if you don't start from stationary, how would it dealing with the non-stationary Y? For Markov process, it's easier because you always can start your solution with a stationary measure. If you're driven by the fraction Brownian motion, which had a big chunk of the history, when you change the initial condition you prepared, you change the system. So you can't use the typical measure starting from two initial conditions. One of the invariant measure, let me converge. And so the analytical aspect is when the slow variables are driven by a fraction Brownian motion. We are not talk about the classical theory. The classical theory of rock path, we take it, we use it, so we don't worry about what it is. But there is still problem. So what is the form of effective dynamics? How would you average it? There are two theories, right? In the case, if you don't have a diffusive in the slow variable, you just have ODE. The classical averaging just say you average out your fast variable, that's your averaged vector field. And then that averaged vector field is a good approximation for my system. And if it's Markov process, you look at the Markov process said you look at how would it converge. It's martingale. You have to compute the variance, the quadratic variation. The quadratic variation is the square. When you average the square, so we're averaging generator. So that's two different types of averaging. So you have fraction Brownian motion here. Which one you're going to take? Now, the other thing is tightness. To prove any limit theorem, first we have to have tightness. Say, is there a uniform LP bound or some bound in some norm of X in epsilon? Now, if it's ODE or SDE, it's relatively easy, especially if I declare F is bounded. Right? You get tightness straight away. There's nothing to talk about. But for fraction Brownian motion, it's not true, because the way, for example, if you take h bigger than a half, the way we define this integral by Young integral or Riemann-Stieltjes integral, the way you have to prove this sum of Riemann integral convergence, we used a Young bound. And that Young bound was saying you take f, remove the initial bound, you integrate it, the difference will be bounded by the whole norm of the integrate, multiply another whole norm of the integrate and integrand. You multiply them together. But if you have T over epsilon, the whole norm blows up in epsilon. So that's why it doesn't work. So tightness is a hard problem here. Okay, so here's my collaborators. Johan is the first one we start to work on this. I gave him the homogenization problem with sort of a fractional Einstein-Olympic process stationary, and see, what can you do? Now, I didn't know much, so I saw that it might be interesting problem. And Johan came in 2018, and he's a really, really brilliant student. Unfortunately, we lost him to Vienna there. And he found out the whole literature, what's going on. Basically, the central limit theorem, or the limit, if you take a law of large number, and central limit theorem has a sort of a functional version of it. So there's lots of such a theorem associated to Gaussian processes with various correlation. And he understood quite a lot of that. And then we sort of clicked on the rough path theory and used the continuous theorem rough path to push it through. And then with Martin, we were working on the slow variable being driven by fractional Brownian motion. I will talk about it. There's two aspects of that. So in this theory, we have one for h bigger than a half. It's like averaging. Then there's h between a third and a half. And that is a weird one. It's like homogenization, but you are actually slow down rather than speed up. So actually, we don't sort of divide your equation by 1 over square root epsilon. You should have to make it smaller. So that one is somehow connecting the standard averaging, stochastic averaging, to homogenization with a whole range of h. So if I have time, I talk about the formulas. Now, Julius, the other very good student here, and is very, very strong student. He understood a lot of things. So when Martin and I just got the paper with fraction Brownian motion, that case, we are aiming to get just a result, something we understand. What is the effective motion? So we took Markov fast motion, or sometimes we took a stationary process. Now, Julia taken the challenge and take fractional dynamics, and he really understood it. So I'll have a talk that for a moment. And Fabian is the latest in this, and he helps us to work out whether, if you look at this process, it's a lot about the invariant measure of this process. Typically, what you do is you freeze the slow variable xt because it doesn't move very fast. You pretend it's just x. Then you have system equations with X. You want to solve how invariant measure. The invariant measure you call mu X. Now, if H prime is half, you have a formula for the invariant measure. And then you can talk about a lot about it. How it depends on X, how it decays and everything. But for fraction-driven process, there's no formula. And so that's where we worked on is to see this averaging object when you replace a small f by capital F of X and Y, and whether depend on X enough. So your effective dynamic driven by this averaged objects have a unique solution. That's what this come in. I only have 15 minutes to see what can I do. So in case not everybody is interested in the slow, fast system, I would like to look into the heuristic of how everything works. And rather, what is the result I put down here is a corollary of a dynamic theorem, the effective theorem. But now I put everything static, so nothing depends on X. So then you see some limit theorem we wouldn't have seen otherwise. So the first one, we know quite well if you take an integral s to t, f of y r over epsilon dr. And so if I look at this one, we typically have an averaging theorem, right? You take integral 0 to t, f of y r dr divided by t, and that converges to f bar. Now, we're not taking integral with respect to dr, we take dbr. So for h bigger than half, the confirmation is that it really behaves like a dr. So this integral converges to f bar, multiply the increment Vt minus Vs. And in the sense that the beta, the Holder norm C beta would converges with this rate epsilon kappa. But the only, so here I'm making my life easy, y is independent of b. And obviously our whole systems are interacting. So they are independent. If you look at it, it converges. But it's not converged as dr. Why? If it, I'm thinking as dr, and this integral makes sense pathwise. I take omega, and this integral makes sense for every omega. I should prove for every omega of b, the integral actually converge in probability. But in fact, okay, that's the open problem.
Sorry, W is Wiener process. What is W?
W. Oh, the next slide. Yeah, the next slide, the W is Wiener process. So that's the first one. For H between third and 1, you look at this typical format for a functional CLT when B is dr. So that's a famous theorem of Kipnis-Vardan. If Y is a Markov process that has certain property, this is functional CLT holds. So this scaling limit of the f along y integrated with respect to r converged to a Wiener process. Here we show it holds, and even after you integrate along the fractional Brownian motion. Now there's two things. If h is smaller, the path is much fast oscillating, right? Is much faster, it's super diffusive. Much more regularly and much is super diffusive. In this case, this one actually always converge without assume f being averaged to 0. Okay? For function CLT, it's always you take the first one, convert it to F bar. If F bar is 0, I look at fluctuation. But for this theory, when H is small, you don't need to assume F to be average to 0. But if H is bigger than half, we already have an average theorem, and we do need it to be centered. I can explain why if I have time, but I thought I have. Any questions? So it's not an easy theorem to think about. I do have people coming to tell me, say it's a wrong theorem. I don't believe it. But it's quite easy to do an exercise on this. Okay. So now let's look at I'm going to look at the dynamical aspects. So it means I try to forget the analytical aspect. I drop the fraction Brownian motion in the slow part or any noise. So we just have random ODE with the random comes from the Y. And Y is nice as you like. And so the averaging principle said the solution is approximated by the average vector field. Now the function CLT is, I already explained, this square root epsilon integral from 0 to t over epsilon FYSDS converted to a Wiener process with some correlation, some variance, which one can write it down explicitly for any function which average to 0 with good properties. And this is one of the signature papers that Kipnis Varadhan and used a lot in random walk, random environment theory. And in this paper, they still assume reversible Markov process. There has been a lot of generalizations in this direction, enormous a lot. For example, Barlingtos and also Komorowski, Ola, and Claudine, they have quite a lot of theories to generalize this. So, but let's go to see the bone of the problem. The theorem, if you look at it, just says, if I look at it dynamically, so that's a static theory, assuming it can be brought to the static theory, to this dynamic theorem, which is the equation that evolves. In that, assume your F bar, your average to 0 for each X, that vector field. Then the process converges to a constant is not interesting. So what you do is you look at a larger time scale. We look at the time scale 1 over square root epsilon. And then this one converges to a Markov process. And this look a bit weird because that's not the usual format. The usual format is in the last bit, that equation, 1 over square root epsilon fxt epsilon yt over epsilon. So that is done easily done by just calling the last object to be the new x. So they'll be equivalent. And then you get the generator written down, given by this matrix sigma. The sigma is given by Green-Cobo formula in the 30s. They wrote this down. You take a fixed x, you fix x bar, and then the first f you have evaluate at the y0, the other one at the yt. Take the expectations of this correlation, right, of these functions. And if this is integrable, then that will give you the diffusion equation theory. What I'm going to say next is if we change y into a fractional object, just the equation dy equals minus y dt plus dbt, bt is fraction Brownian motion. And then you take that object, and this integral may not be finite. if your F bar equal to 0. So F bar equal to 0, the average equal to 0 is not enough. Now, what happens is the F bar equal to 0, I again want to go back to QLC expansion. You take a L2 function with respect to your Gaussian measure, you can write it down as QLC expansion, the average plus an integral, and then the iterative integral and so on, right? And then average equal to 0, this means the first term disappeared. And let's call that a Hermit rank 1 function. It turns out, of course, you could have more terms disappear. I could take a Hermit polynomial, which means, I'm on the degree m, all the previous disappear, that's a Hermit rank m. It turns out if the fraction part does not allow it to go fast decay enough correlation, you can always increase the complexity of the function itself, assume a higher Hermit rank, and together you could have some finite object. So that's what Johan did. So we just take the stationary fractional OU process. I'm running out of time, I have 5 minutes. So we were able to take a process of this form. So a function of x multiply function of y, and you try to decide what's the correct scaling coming from the last formula computation. And then we show this convergence. They would be converged to an equation driven by the limit of you put the epsilon minus alpha k and gk together. If that one converges in the rough topology, the solution converge. But this could converge to a Wiener process, a fraction Brownian motion, a Hermit process, depend on the mixed property between y and g. And I should say there's lots of people who done this theory, has used rough path before, and I don't think I have time. So the paper Johan and I wrote is still under review, and there was a teaser paper. Now, the other theory is what if it's non-stationary? And the non-stationary, there's lots of problem because it's non-Markovan. And the one problem was definition of you could say it's invariant for each time t. The measure is the same, but it's not enough. You could use random dynamic system that's also pitiful, but there is a theory about it, was put in, is in HERA 05. And what happens is you try to lift it up to Markov process, not on full path, but only the 0, sort of only the from minus infinity to 0. And then you take an invariant object upstairs and project it down. And so anyway, so the geometric convergence is not known. And Julia was able to prove it. So we have this paper here together. And what geometric convergence improved some result of Hera, Panloop, and Richard. And also with Fabienne and Julian, we also was able to manage to prove some smooth dependence of the invariant measure and the kernels and so on. Finally, I think I only have 4 minutes, maybe 5 minutes to, yeah, 5 minutes. So to dealing with the work with fractional averaging, I call it, when your slow motion is driven by fractional Brownian motion, and the fast is by Markov process. The fast driven by fractional Brownian motion was dealt with the paper of Julian and myself. And so, but that's a sort of a different technique a little bit. So again, we've seen the limit theorem for h bigger than half. It seems to look like ODE rather than SDE. And so the theorem is the following. So we want the concept rather than the precise, the best result. So under some conditions, the solution x epsilon as a process converges in probability to an equation like this, where you average your vector fields in a naive way. You just average it, you don't square it or average. So it's average. And so there's an open question still whether we prove the annual convergence, whether there's a sequential convergence. The difficulty in this one, there's lots of difficulty, and we use a Lewis stochastic sewing lemma to dealing with this mixed equation to give it a very good estimate. And so it was very pleased with that. And of course, the Lewis stochastic sewing lemma is now taking off in a big way. And with Julia, we also have sewing lemma, quantitative sewing lemma for SPDE and the proof for SPDE. Now, let me give you the formula for h between the third and a half. For between h third and a half, you still want to do averaging theorem. But what I do, I just do a preliminary calculation when the Fi doesn't depend on x. You see this formula, you have epsilon 2h, but you have double integral 0 to t over epsilon. So that means that this object is at the most best of all the epsilon 2h minus 1. So it blow up. And if the blow up, we rescale by the rate of blow up. It turns out, yes, this equation does converge for h smaller than half. So then you want to ask what happens with h bigger than half. H bigger than half in the kernel, this guy is not integrable. At infinity, you have to remove it. The way to remove it is assume the function average to 0. So we're back to stochastic homogenization. And so this is about the last slide. The theorem is the following. The solution converges to a Cooney type SDE. And it's not the solution converge, it's the whole stochastic flow convergence. It means you started from different initial point, jointly converge. I think that's new, even for general averaging or homogenization theorem. And so the Gaussian field is given by this formula. And this formula is, you have the Fk, forget you have k, that's F, the L to the minus 1 and 2h, Fk. If h is a half, that's the stochastic averaging theory. Your 1 minus 2h is 0. That's just the averaging result. If h is equal to 1, you get minus 1. That's exactly the homogenization theory. And so this is just the basically has smashed all the theories together. We use different proofs, but we have some confidence. It already gives some good proof for averaging, but we have some confidence that could be quite unified in this front. And so I think that's it. So basically, we haven't been able to show the super diffusive one slow down to diffusion and the super diffusive one and speed up to a diffusion. And I just want to say this equation doesn't a priori make very good sense if you have y there. If you don't have y, it's understood. So we have made sense as a certain limit of Gaussian objects of that. Finally, I just want to give some credit to people as well. And there's lots of people has been working on slow, faster system, including Inahama, Bien, Schmufa, Bugan, Gallia, and Spilino Plus. And the difference between what they have and what we have It's mainly somehow in front of fractal Brownian motion, they don't have the fast motion. Sometimes they don't have, if you don't have slow, you just become a process itself as a limit theorem I gave you. If you don't have a fast, it doesn't blow up. So it's a different theory. I think that's it. Thank you very much for your attention.
Right. So yeah, thank you for that nice talk. So we can give a Zoom applause. So we definitely have some time for questions. So you can either just unmute yourself, or if you prefer, you can type it into the chat.
So that sounds like being either totally incomprehensible or totally clear. I think I don't.
I had one question.
Yeah.
I think so. There's a kind of regime where these things kind of generate. So you generate kind of new noises, right? So you kind of build things that are kind of not measurable with respect to the original things that are driving the system in some of these rough regimes, right? So one question I had is there kind of any physical maybe it's an open-ended question, but when you're in problems where you kind of lose the pathwise nature, is there any physical manifestation of that?
It's a very good question. It's something quite a few of us is trying hard to understand that. So what exactly going on? So the loose pathway property is the one I call the annealed result, with borrowed terminology. It's really you average your environment same time as your own system. But what we do want is quenched, you fix a path. I don't know. We start to think maybe there might be a quenched one. But don't quote me. This topic is starting, I would say, because our conditions are quite rough, and lots of topic for this one. I could use like with Johan, with using stationary process. We haven't used non-stationary one. And so there's a lot of things that are still to be worked on. And we also hope there's lots of other candidates processes in the rough differential equation domain to work on, not just the fractional Brownian motion, some process with other interesting properties. Like Johan did have a function CLT for Hermite processes. But then you still, there's a lot more to work. And so in the, for example, in the Johan's, that paper with me, when you take the homogenization, your process is a fractional Einstein-Uhlenbeck. In principle, if you look at so much literature, if you put, that's what he did, he put everything together into the same platform. And but then before that, the CLT theorem is always converges in distribution. Everybody's interest converges in distribution. Then the final click coming from Martingale convergence theorem for diffusion creation. But now you don't have that theorem to use in this case, and it's become very much important to use the rough path tool. And we use this, this rough path, really started to play a role here, the continuous state theorem in the rough path, which allow us to think about the central limit theorem from a different level. So we start to think not as CLT in distribution, it's convergence in Holder norm. When we did the Tower model, then of course, then we start to look at rough path topology. So it converges in Holder, but then the iterative integral also converges some kind of some C, some R, sort of Holder type norm. So that's basically, and all of this limit theorem I never thought about before they start to come in. And maybe one can explore them with other processes. That's what I hope.
Hi, Xue-Mei.
Hey.
You hear me?
Hey, Yuri.
Actually, at the beginning, I was a little bit confused. You wrote your equations where fast motion were dependent also on the slow one. That's how Hasselmann actually wrote his equations, because we know that the weather depends on the climate. Climate is a slow motion, and we all know that climate changes and we have all these terrible weathers. So, but after that, I worked on that. This is a more difficult situation, and after that, you just somehow waved a hand and considered fast motion as a separate, separately defined diffusion or something else. And then, so this is okay, but I mean, the real question is when you have what's called a fully coupled system.
I did a lot of cheats, yeah. The one for h bigger than half is fully interaction with them. So yeah, so whether, as you said, the weather depends on climate, but the climate is influenced by weather slowly as well. So that's why that's a fully interactive. But some of the ones we are not able to do fully interactive ones. But in any case, I saw that I want to put the message through what should be the end result. So I just simplified the fast motion completely into a stationary object, completely as good as we want in the talk. Yeah.
Okay.
But in the fully interactive case, there's a lot of estimate gets harder. That's where we use this beautiful stochastic sewing lemma. And we also use some Gaussian moments, like cumulant and so on, to work with. The other thing, you are expert on this manifold as well. That's the next one.
Yeah. Okay. Probably we'll meet in Maryland and we'll talk about it.
Oh yeah, see you there.
Yeah.
Next week.
Yes.
All right.
Wish you a good trip.
Thank you for the questions. We may have time for one very quick question, but then otherwise we should transition to our next talk. Oh,
Professor Li,
Yeah.
I curious for the non-Gaussian Levy noise driving slow fast system. If we let go of the moment, could we also can get some limit or like the fractional bar motion case?
Could you
Levy
repeat?
case.
Yeah, could you repeat again your question? Sorry.
I mean, for the fractional bar motion case, you get the limit maybe from motion Wiener process. If now is non-Gaussian Levy noise, could we also can get some limit in the slow fast system?
Yeah, that's a good question. I think that's I would say this is the beginning of whatever you want to work with, whatever you think interesting. But there are, I think there's certainly something you have to pay attention. I would think a self-similarity is very important. In fact, if you take the homogenization theory, and when I'm not sure which integral you're talking about, if you talk about the integral 0 to t of dr for function evaluated along the path of a fractional Orenstam Erlenbach process, if you're talking about that one. And that one can give you, you started with fraction Brownian motion driven equation, you can give you in limit, yet you do have Brownian motion, you do have fraction Brownian motion, you do have a Hermite process. But if you put them together as one class, that's it. I think that's it. Whatever you're driven by this mix of processes in the limit, that's the class is preserved by the limit. So that's what I believe.
Mm-hmm. And for the manifold, if you get the manifold in the slow fast system, does this manifold is potentially tracking property?
Well, what a property tracking?
Is potentially tracking property.
Could you explain?
It means the other trajectory is potentially goes to the manifold, is potentially tracking property.
Oh, I see. Yeah. Okay. On manifold, there's two things which you have to worry about. One is how do you obtain an interesting slow fast system? And that if you have a invariant manifolds, that type of thing, you could put a bit off. So that's how you would get it, but it's lots of work to get a nice one. But if you already have a slow and a fast equation, the biggest difficulty with manifold is, as you know, most people take a coordinate saying that's coordinate, that's the same as manifold. But if you do estimate involving especially long time, this sort of thing, it's harder. I think for manifold, it's always harder to do quantitative estimates.
Okay, thank you.
You have to have some thing to play with, like I did work things like a group, Lie group, or homogeneous spaces. They are good space to work with because you can track your equations, you can solve them. Yeah. Thanks for your question.
So thanks, everyone. I guess we'll transition to the next